Okay, so lesson number 2 here in unit form, substitution method. So we're still solving our systems of equations, and we refer to them as systems of equations because they are linear equations, and we've got 2 of them that are there. So that's why they're called systems of equations. So the idea here is the substitution. So let's talk substitution first. It's in sports, where we have a sub that sits on the bench. So we substitute. Someone comes off the court, someone goes on the field, if you will. In school, we've got substitute teachers. So, Mr. Savage in here today. We have a sub today. So again, someone that's in my place. So that's what we're doing here is we are putting something into its place. So in order to do that, you do need to isolate one variable. So look at problem number 1. We have an example here. The y. The y has been isolated because it's just y equals. It could be x equals, that's fine. But again, that's where it needs to be isolated, where it's just it by itself. And then the idea here is, like it says, it's substitute the information into the other equation. So here we know y equals x plus 5. So what we're going to do is we're going to go to where the y is at in the other equation, and we're going to replace it with the x plus 5. All right, so let's do it here. All right, so we've got 3x, we've got our plus, and again, we're plugging in, we are substituting in the x plus 5, and then we have the rest of it equals 25. So again, if we kind of look at it, the 3x is still there, the plus is there, there's no longer a y because y equals x plus 5. Wait, so then we just solve. 4x, all right, let's subtract the 5 over. 4x equals 20, divide both sides by 4, so yep, x equals 5. All right, but remember, we're solving for both of our variables here. So since x equals 5, we just go into one of the equations and we use it. So we'll go back to one of the originals. I'm going to choose the first one here because, well, there's not a lot going on with it. It's already been isolated there. So when I plug in my 5 for my x, y equals 5 plus 5, and sure enough, y equals 10. Now, we still write our answers out as ordered pairs. So we still want to get the idea of, yeah, it's the ordered pair 5, 10. Now, if you did write out x equals 5, y equals 10, you would just put them right next to each other and box them in there. But again, writing it out as the ordered pairs, that gets the job done there. Okay, let's take a look at problem number 2 since it's right there. In this case here, we don't have a letter that's been isolated. I don't have an x equals, I don't have a y equals. Now, it doesn't matter which equation I use as long as I can easily rewrite it into x equals or y equals. So I've got a few options here. For example, in the first one, I could add the y over. Okay, and then I would get x equals, and then we'd have a y minus 2. That's fine. I could go to the second equation, and I've got the y by itself. I could subtract the 4x over. So then we'd have y equals, and then we'd have negative 4x plus 2. The y would be isolated. So it's not going to make a difference here. I just like to start with the first one, and I see there's a plain old x, so I'm going to add that y on over. So yeah, it's x equals y minus 2. I could say negative 2 plus y. They're all equivalent expressions. So we're just going to plug it in. All right, there's the x. We're going to plug in the y minus 2. Now, what makes this one a little bit more interesting is we have the 4 up against it. So 4 times, and it's not just an x. That's why the parentheses are there. It's a y minus 2. And then I've got a plus y, and then an equals 2. So when you do substitution, you're always going to go from 2 variables, an x and a y, down to just one variable, just y's. That's the whole point of substitution is we can't solve equations unless we just have one type of letter. In this case, we've got just the y's there, so we're ready to go. So 4y minus 8 plus y equals 2. The 4y with the y, so that's a 5y. Let's add the 8 over. There's a 10. 5y equals 10. Hey, y equals 2. All right. Go back to the original problem there. Now, again, it doesn't matter which one I use. I can just grab the first one that's there. So in this particular case, when I plug that on in, it'll just be an x minus 2. Again, we're just plugging it in. It said x minus y, but y is 2, and then equals a negative 2. So let's add the 2 over, and yep, x equals 0. So I've got the order pair 0, comma 2. Now, remember, we can check, all right, and by plugging it in, we should get true statements. So if I plug in into the original one, plug in my x minus the y, which is a 2. 0 minus 2, does that equal negative 2? Yeah, it does. So that's good. Let's check the other one. 4 times 0, well, that's 0. Plug in the 2 for the y. So 4 times 0 plus 2 equals 2. Yeah, 4 times 0 is 0. Does 2 equal 2? Yeah, it does. So again, no, I've got a winning answer. So substitution's nice. From the check step, it's the same idea behind it. It's just that when we substitute at the beginning, you're typically plugging in more information than just one particular number that's here. So let's find someone else that's good here that's going to help us kind of grow here a little bit. Ooh, 3 is nice, actually. So check this out. Like, I see the y in the first line that's here, but it's a negative y. So, like, I could subtract my 2x over, and I could then, divide everyone by -1, so I get it into a y equals. That's fine. That does the job. But we do want to show you another technique. And if you look at the second equation, like the y is kind of by itself. So one of the things I could actually do here is I could just divide everyone here by -3. All right. Then when I do that, that gets me a plain old y. All right. So then equals a 2x and then a -6. All right. So yeah, I mean, you could. Now, the only reason why I'm doing this here is because I can divide them all by a -3. I don't want fractions. Okay. So if I couldn't do fractions, I would play with the top one and rewrite it into a y equals. But okay. So let's go, because I rewrote this guy. I now need to plug it in to the other one. So I've got a 2x, I've got a minus. Now, again, when you have to plug in more than one person, we encourage you to use your parentheses. 1, because we had to see with the distributive property, or 2, this minus sign is actually going to come into play here. So check this out. This subtraction sign has to go to both of them. We still distribute it. So it's a 2x minus a 2x plus a 6 equals a x. And like, oh my goodness, but by x, does 6 equal 6? It does. Remember, when all your letters go away, if we have a true statement, we have infinite solutions that are there. So yeah, anything's going to end up working when we plug it in, because really what it is, they're the same equations. That's what end up happening. Like, go back up here to the beginning. If I subtract my 2x over, I get -y equals -2x plus 6. I divide every one by -1, and look, you get y equals 2x minus 6. Y equals 2x minus 6. Y equals 2x minus 6. So no matter what we plug in, it's the same equations. So it's infinite solutions. So we can just say infinite solutions. If you wrote them out as ordered pairs and you did the infinity, common infinity, that's fine. If you said IMS, infinitely many solutions, that's fine. If you said infinite and then added in, like, listen, people, as long as we're saying it, we're good regarding it. All right. So that's good. That's good. Ooh, let's turn the page here. Let's turn the page and let's go after someone like problem number 7 here. All right. So we've got Jack's Jungle Gym. Charges $12.50 for admission and 75 cents per ride. Patty's Place. Who writes this stuff, right? Yeah, exactly. I think it's a criteria to make it kind of corny that's there. Charges just $18.50 for admission and then 50 cents per ride. All right, so for what number of rides is the cost the same at both parks? Okay, so when they're saying the same, that's what we're solving. We want them to be equal to each other. Now, the idea behind this and what we'd really like to be able to see is like, okay, which place is cheaper based on the number of rides. And that's a good application of it. Like, if I'm going to go on like 20 rides, does it make more sense to go to one place versus the other? But this one's saying, hey, for what rides is the cost the same? So writing the equation here, what we're going to end up doing here is just going right into y equals 75 cents per ride. That's our slope we're looking at. And then $12.50 for admission, because that's the initial amount. The other side to it is, well, we're going to have the exact same thing as well, because, well, it's the same scenario. 50 cents per ride, and then they're going to charge you a flat rate of $18.50. So, yeah, we just set them equal to each other. And the nice thing about it is, it's like they're telling me what y equals. So we're going to, if this is what y equals, we're just plugging it into the other y. So, yeah, we get this equaled to that. So again, the mindset there is we want to know when they're the same. That tells us kind of like, listen, let's just set them equal to each other because we know they're the same. But again, your substitution also shows, hey, we can plug this in for the y. So subtract the 50 cents over, you're going to get 25 cents, which means I'm going to subtract the 17.50 over. All right, that's $1. Divide both sides by 25 hundredths. How many groups of 4 to make one whole? It would be 4. All right. So 4 rides is when it won't make a difference. And then we can get to analyzing, well, what if we do more than 4 rides? Who's cheaper? We do less than. And that's where the graph is nice, because it gives you a visual representation of that. So, all right. Yeah, no, I think we're in a good spot regarding it. The main thing is plugging it in. Just to take a look at problem 6 here, we're already isolated. Wonderful. We would just plug it on in right there. Whereas in problem 5, I'd be focusing on this y right here. So I would subtract my 2x over. So I get y equals negative 2x plus 3. And then again, we are substituting it in for your y right there. So yeah, there we go, people. See you tomorrow.